One of the first proofs they show you is in this text is the proof of the Archimedean property, which says if a and b are positive integers, then there exists a positive integer n such that na is greater than or equal to b. What they don't do is prove that directly. They don't start with a and b being positive integers. Instead, they start their proof by saying na is less than b. So they have an if-then statement, and they start with the then being false. So I wanted to go over how this works with you, and this is called a proof by contradiction. So I'm going to stick with just stay out of the math for a minute and just look at the truth tables and see how this works. So what I'm starting with is two basic statements. It is raining is statement A. B, I'll carry an umbrella. So what we have here is an implication statement. A implies B. This is an implication. And it's what we call an if-then statement. If A, then B. So using the two statements I actually gave you in English, it would be if it's raining, then I'll carry an umbrella. So we're going to look at the logic behind this implication. If A, then B. So what I'm going to do is look at all four possibilities for A and B. You might think, how are there four? Well, A can be true or false, and B can be true or false. So true, we're going to show with a 1. You could also show it with a T for true, but generally we go to the 1s, and then for false, we use the 0, kind of like binary, back into the computer systems, etc. So a 0 or an F. I'm going to use 1s and 0s. So one possibility is that A can be true and B can be true. Or A can be true and B can be false. Or A could be false, B could be true. Or they could both be false. And that's all four possibilities for statements A and B. When we have a compound statement, we do A implies B. I'm going to add just another column to my truth table here. What I'm making is a truth table to show you the logic. And I'm going to stick with English for a minute. If A, then B. So A is true, which means it is raining, and B is true, I will carry an umbrella. If it's raining, I'll carry an umbrella. Was my original statement. Both are true. A implies B is a true statement in that case. On my second row, it's raining, but I don't have an umbrella, which clearly contradicts my statement up here that says, if it's raining, then I'll carry an umbrella. It's raining, I have no umbrella, it's false. The last two are kind of tricky, and they confuse people sometimes. So my statement was, if it's raining, then I'll carry an umbrella, but A is false, so for both of these, it's not raining. So you really can't say that I lied. It's not raining and I have an umbrella. This statement is not false. If it's raining, then I'll carry an umbrella. It has nothing to do with what happens when it's not raining, which is one of the tricky things in math. You really have to consider both directions for this. So since it's not raining, you can't prove me false, so both of these are actually true. And this is your standard truth table for an implication statement. The only time that it can actually be false is if you start with your if being true and your then being false. In all other cases, the implication is true. So this would be what you're doing if you're doing a direct proof. You'd start with A and then take the steps to get to actually B. On a proof by contradiction, they actually look at the contrapositive of if A, then B. And the contrapositive is if not B, then not A. Okay, and I'm showing the nots with bars on top. You can actually just write not A, and that could be, that's fine. You can do it with the bar, and I've seen it also with the tilde in front. So either one of those is fine. I like the bars because it's simple. So if not B, then not A. For some people to keep track of everything, they'll actually go through and do the columns. So I'm going to do a not B column and a not A column, which will be the exact opposite of the A and the B column. So for not B, since B is true over here, not B obviously is false, and we're just going to swap the 1s and the 0s and do the same thing for the A. And that just keeps it straight for some people. The less you have to keep in your head, sometimes the better. How much you include on a truth table is totally up to you. It's what you need. So we've talked about the implication. The only time the implication is false is if you start true and end false. So we are going to start true and end false right here. So that is false. All other possibilities are the same. Now look at the two columns of the truth table. A implies B, and not B implies A. They are identical. Since they are identical, proving this is the same exact thing as proving this. That's not true for every statement. The contrapositive and the implication match. They always match. But if I had done the inverse or the converse, which you start with your implication, A implies B, and you have different possibilities of this. You have where you can switch, B implies A. These two are not equivalent. Or if you do, not A implies not B. These two are also not equivalent. If you actually look at these two, though, they are equivalent, and you can show that with the truth tables. So the inverse and the converse are equivalent statements logically, and the implication and the contrapositive, are equivalent. So this is what they do. So for the Archimedean property, they start with a false assumption. They do not B. So they will say NA is less than B as the starting, and I will go through that proof in the next video.